So, today's lecture, we are going to study about titration. It's a very short topic, so I guess it won't take much of our time. Now, before getting into in-depth resolution for this titration, what is this term titration? It is basically a process where we do chemical analysis, where based on, let's say, a known substance, the information for a known substance, okay, from a, let's say, based on the information from a known substance, we calculate the information for the other unknown substance. So let's say here is an example. Let's not consider the amount over here, this concentration, let's don't consider here. But let's say we have HCl of 25 cm cube here of any certain concentration which we don't know, let's say x mole per dm cube. Now there in the in the conical flask we have placed the HCl. Now in the burette we have placed, let's say, sodium hydroxide of 0.7 mole per dm cube. Now the starting point, the initial point, from here it is, let's say, 0. It could be some other value, but we just need to find the difference, like the portion which has been used. So the tap is open and the droplets of the sodium hydroxide, it adds to the conical flask and the reaction happens. So we can see sometimes the color change happens. This is because, like, when we apply what do we say, reagent, uh, colorized or like color recognizing reagent, which we often say, uh, the reagents which could be used, like for example, phenolphthalein, methyl orange. So those are the reagents, or more precisely we can say the indicators. So that indicators helps to recognize or helps to form the color from for one form to another. Now let's say the starting point is 0, and as the reaction proceeds, the drop adds, and we start to shake the conical flask as the droplet adds there, so that the whole mixture, like the sodium hydroxide, get mixed with the whole mixture of HCl. And this red color, it starts to vanish because all the sodium hydroxide and NaHCl actually they reacted. Now about the methyl orange or any indicator that actually has different color in different pH value, not when they are neutral. So let's say, in some, let's say there's an indicator, that indicator uh, shows certain value in acid, shows certain color in acid, then shows some other color in, like, neutral, and some other color in base. Now let's say the reagent shows color, like has colorless or colorless state in, or shows no color in acid. So we have placed the reagent in the HCl. Now when drop by drop the droplets are added, the neutral portion also has, like, no change, like there is no, like it also has color test. The reagent in the neutral state also has color test. Now why I am saying about neutral, because acid plus base, they tend to have a neutralization reaction. So at the moment when the drop adds, at the very concentrated part, obviously there is, like, sort of a neutralization reaction happens. But as soon as that sodium hydroxide gets mixed with the whole of the HCl, the sodium hydroxide does not have any effect because the HCl is comparatively much more greater in amount. Now, as the drop adds, initially there is sodium hydroxide, isn't it? And let's say we know in sodium hydroxide this color, the reagent's color is red. So at the very instant, the reagent tends to show a pink or red color, which indicates that, okay, like it's working, and so the sodium hydroxide is being added. Now, drop by drop, when the droplets are added and the conical flask is swirled, if the reaction proceeds after a certain time, for for just one single droplet change, the color will change completely. That means the full neutralization reaction has occurred. Now the solution has just one more droplet of sodium hydroxide, just a single more droplet, then the quantity of acid. That's what it presents, like that's what is the end point for this titration. And we just turn off the tap immediately and focuses on where the this liquid mark or the sodium hydroxide level has come to, and we record and take note of the mark or the value, Then we calculate the difference between the initial and the start, like the initial and the final point of sodium hydroxide. That's the volume. So let's say in this case, the required volume of sodium hydroxide is 17 cm cube. Now we know already the concentration, which we will usually know, because this is the known substance which we are using in order to analyze this unknown amount of HCl. So 17 cm cube and 0.7 mole per tm cube. Now if they react, we can obviously write the react equation for them, which is sodium hydroxide plus HCl equals to NaCl plus H2O. Now we can simply do molar ratio and find the concentration, like the at first the mole of the HCl being used, because we can simply calculate the mole from here. Then we can do the molar ratio. After doing the molar ratio, we do have the value of the volume, and we can use the simple concentration formula, because after molar ratio we do have for HCl the mole as well as the volume. So we can do molar ratio in order to find the concentration for sodium hydroxide. And if any other calculation is being needed, we can use this analysis. So this is actually the main part of titration, like which happens here. Now, if we try to define like what type of titration usually happens or what type of analysis we do usually do, there are, like, we can categorize them in four different sectors, of which one is between strong acid and strong base. So we can do titration between these two types of substance. The second type is strong acid and weak base. Then the third type is weak acid and base, sorry, strong base. And the last one, I hope you've got it already, which is weak acid and weak base. So these are the four type of like titration uh, category we can actually make use of. Now, coming back to the diagram here, let's do some calculation in this part, so that like it becomes easy and helpful for us to actually know what type of equation, what type of question like do they give in the exam, in the exam papers. So let's say this is the, like, okay, that's not fine, this part. Okay, I will say what to do with this one. I will later on discuss about this. But yeah, for now, let's do the calculation part. As I mentioned, these are the like given information to us, and let's say the required NaOH for the complete neutralization reaction is 17 cm3, which means that actually the last point or the final point for from this burette which we got, which is 17 cm3. Now, based on this, we can do some calculation to calculate the mole for sodium, mole for NaCl. So step one, we can at first find, okay, in order to calculate the pH value, let's say our calculation, like the most of the time, what type of calculation they give you the concentration for, let's say, this solution initially, which is this one. So if the initial concentration of HCl is given, we can obviously find the initial pH. So step one is to find the initial pH. How can we find that? We know H, like in HCl terms, like if we do complete ionization, we have what, H plus Cl minus. So we can say from every HCl we get what, 1 mole of H plus. So that means in 1 mole of HCl there is 1 mole of H plus. So the molar ratio between HCl and H plus is 1:1. So that means the concentration of H plus is should be also be H as well, like the HCl. So in step one, we need to find the initial pH. Initial pH, which is going to be what? The negative logarithmic function with base 10 of H plus concentration, in this is 0.5. So if we use that, we should be getting somewhere around 0.3. That's the initial pH, which is actually like very high pH value, like sorry, very low pH value, which means it's very acidic. The acidity is very much high. The pH is low, but the acidity is very high. Now the step two is or as the reaction proceeds, obviously the pH is going to like increase. Why? Because neutralization reaction happens. So HCl is being used up, sodium hydroxide is added. So with time, we can say that if this pH is, let's say, over here, initial pH value, let's say this is the pH chart, like in this axis, and this is, let's say, the volume for sodium hydroxide. Initially the volume for sodium hydroxide is zero, like in this conical flask, isn't it? Initially HCl is at maximum 25 cm cube, so sodium hydroxide is minimum in that, at that point. So let's say here, initial concentration, sorry, initial pH of the HCl in the conical flask is this, which is 0.3. As we sodium, like, add sodium hydroxide, what should happen? Like, what do we think? Obviously the pH is going to increase. Why? Because HCl is being used up. So like it tends to go towards the neutralization, isn't it? The neutralization reaction is happening. Let's say if it's 0.03, it is 0.3, and this is 7. That means the pH will slowly go towards like the pH 7, isn't it? It will try to go towards pH 7 as the volume for sodium hydroxide increases. Let's say drop by drop, if we are adding. So after, like, at a time when it is 17, obviously that is going to be near about pH 7, isn't it? Because 17 cm cube is the required volume for the neutralization reaction. So somewhat this way the reaction should proceed, isn't it? So yes, obviously in that way the reaction is going to proceed. So let's keep on going with our calculation. Now the step 2 is to find actually the volume for, sorry, the mole for HCl which is being like neutralized. Now how do we find that? We can find it in the above process. If it says 17 cm cube of sodium hydroxide being required for the complete neutralization reaction, we can simply write the equation again, and we will get NaCl plus H2O. Now from here, if the equation is balanced already, we can do the molar ratio part. So we can calculate actually the constant, like using the concentration and the volume of sodium hydroxide, we can say 0.7 concentration and volume is given 17. So mole will be 0.7 into 17 divided by 1000, which is 0.0119. Now, after doing the molar ratio, we would get it's 1:1, so HCl is also 0.0119. Now, if that's the case, then we can say that the mole for HCl is this one, and the volume of 20 for like the HCl is 25 cm cube. So from them, we can actually tend to find the concentration, which is, which would be, let's say, 25, 0.0119 mole divided by the constant, the volume, into 1000, which should give us 0.476. So this is, let's say, at the neutralization point, isn't it? At the neutralization point. Now comes the twisted part, where, let's say, the volume. Okay, before doing that, the initial portion, like, if before doing this part, we can do one more thing, which is, let's say, let's do this part on the later part. Let's do this part at first. That the amount of HCl which is initially, because we have already the concentration for HCl over here, isn't it? So we can directly calculate the concentration in this portion. So step 2 is, let's to find the initial mole for HCl. Okay, or initial, or we can say the number of moles for HCl, because that like the like amount of HCl is not decreasing. Like amount of HCl is remained constant, because HCl is not being like dropped, isn't it? Like added drop by drop. Rather, sodium hydroxide is, the amount of sodium hydroxide is increased time to time. So we can simply calculate this by what? By using this the concentration and the volume. We would get the value to be 0.0125. Isn't it? 25 into 0.5 divided by 1000. So this is the mole for sodium HCl. Now that means this much of HCl needs to be neutralized, isn't it? Now, if we write this was the part, like in part two, we need to find at first this one. Now, let's say we don't know actually how much sodium hydroxide is required. I've just said let's say 17 for the like approximation part. Let's say we don't know actually how much NaOH is required. We need to find how much NaOH is required. So we can simply use this equation instead, which we did like in the other way. In usual titration, what do? We need to find this HCl's information, isn't it? The concentration for HCl, we need to find it. So in order to do that, we need to calculate the information from NaOH, then we need to come towards HCl. But now over here, already HCl's information is given. So we need to do a reverse process to find how much of sodium hydroxide is required. So NaOH plus HCl would give NaCl plus H2O. Now, since the mole of HCl is 0.125, the molar ratio we can see is 1:1, so the HCl is to sodium hydroxide, so the mole should also be 0.125. Now, if we find, like if we try to find how much sodium hydroxide or how much volume of sodium hydroxide is being used, we can use the formula concentration equals to mole by volume into 1000. From here, we need to find just the volume. So volume is going to be what? Mole over concentration into 1000, which is 0.7 from over here, which is given already. Concentration, sorry, mole is 0.0125. I'm really sorry for that. Divided by concentration, which is 0.7 into 1000, which should give us 0.7 times 1000. So yeah, it is actually close. Like the approximation was actually close. So 17.857 cm3. So this is the volume for of sodium hydroxide which is needed for complete neutralization reaction. Now let's say the sodium hydroxide provided was 25 cm3. Okay, like this is the amount which they're giving us. Let's say the full 25 cm3 is being added. Required sodium hydroxide, instead of required sodium hydroxide, let's say it says total NaOH applied 25 cm3. That means the excess amount is which portion? Is 25 minus 17.857, isn't it? Because this much is used up in the neutralization reaction. The additional portion is the excess, isn't it? So that's what we need to find now. Like over there, in that excess amount, what is the concentrate? Like what will be dominating in this solution? Obviously, sodium hydroxide is being added. So the after neutralization, since more like excess sodium hydroxide is added, the solution will tend to become like basic, or the alkalinity increases, isn't it? So the concentration for whom will increase, H plus or hydroxide? Obviously hydroxide, OH minus is going to increase, so pH is going to increase, the pH value is going to increase. So if we proceed, okay, this was the actually like step 2 part. This was the like to find the required volume for neutralization. That was part 2, step 2, and the step 1 was like the finding the initial pH. Now in step 3, let's say we can try to find in step 2, which we can try to find like the portion of the excess sodium hydroxide after like if we subtract the actual volume which of sodium hydroxide being used, which is 25 minus 17.857, we would get 7.143 cm3. So this is the amount of excess sodium hydroxide. So now if we try to do the ionization, which is Na plus plus OH minus, we can get the concentration of hydroxide by doing molar ratio, isn't it? Since we can see the the molar ratio is 1:1, so simply we can say the mole for NaOH is equivalent to the mole of sodium hydroxide, isn't it? Because similarly the concentration is this like same. So in our step 3, the actual thing we need to find is the concentration of excess sodium hydroxide. How can we do that? We can do it by doing this at first, the let's say we have from here, as we can see, the initial. Okay, one thing we need to, like, obviously we need to find the concentration of sodium hydroxide, but how we are supposed to, because try to see from the given information what information can we get for sodium hydroxide. We can say the concentration is 0.7, but no, this is the 0.7 concentration for the 25 cm cube, like whole 25 cm cube. But after it is being added, this 25 cm cube is being added to the conical flask. Already there was a 25 cm cube of HCl, isn't it? So HCl 25 and the addition of sodium hydroxide of 25 cm cube. So 25 plus 25 what? 50 cm cube of solution, isn't it? That means the concentration is going to change, because before it was in 25 cm cube, now it's in 50 cm cube. So obviously it is going to change. So what can we do is, we know the NaOH is what? The mole being used, which is 0.0125, which we found in step 2. Now, can we somehow find the total amount of sodium hydroxide, the mole? Obviously we can, because we have the concentration and we have the volume which are being used. So we can use that. So initial mole or total mole of NaOH, total mole of NaOH is what? It is 25 into 0.7 divided by 1000. This should be 0.0175. That's the mole for sodium hydroxide total. So that means now the excess amount of mole of sodium hydroxide is what? Like the difference between these two, the total and the amount being used. So excess is equals to 0.0175 excess NaOH minus 0.0125, which should give us 0.0050, isn't it? Yes. So now we have the amount of sodium hydroxide in excess, that portion which is in excess. So this is actually the part which is in excess, 0.05005. Now we need to what? To find the pH for the final result actually. But we don't have any more HCl, sorry, H plus. We don't have any more acid. So the alternative is to find the pOH, isn't it? Because we know pH plus pOH is equals to 14. So from that equation we can find the pH value. So we need to find pOH now. But how can we find that? We need to find the, like, the concentration for OH. We have the mole for NaOH. That means we, by simply doing molar ratio, we can find the mole for OH minus, which we can see actually the molar ratio is 1:1. So the mole for OH minus is going to be 0.005. That means our mole for OH minus is equal to 0.005. If that's the case, then concentration is going to be what? Mole divided by volume into 1000, isn't it? Now, what is the volume, amount of volume? Not 25, rather 25 plus 25, the full concentration, the full solution, which is 50. So 0.005 divided by 50 times 1000 should give us 0.1. That's the concentration for OH minus. So this is our actually step 4. Step 3 was to find the excess NaOH. Okay, the mole for excess NaOH. This was for step 3. This is step 4. This is step 4, which is to find the concentration for OH minus. So we found the concentration for OH minus. Now step 5 is to calculate the pH. So we can find at first pOH, which is negative log H10 of 0.1, which should give us a value of minus plus, wait, yeah, so it should give us a value of positive 1. That means pH plus 1 equals to 14. Therefore, the pH value is equals to 14 minus 1, which is 13. That's our what final pH. So initial pH we found 0.3. Final pH was something like the mid pH was 7, like the neutralization part, and the final pH they gave us 14, isn't it? Now we can obviously say the pH is going to increase like this there and this, like as the constant, like the volume of NaOH is 17.9 or 17.85, 875. There is the pH of 7. Then as the volume increases, the pH increases until it becomes like the volume is until the end, which is 25 cm2. But actually, yeah, the increasing pattern, the graph will be an increasing pattern, but actual shape is not like this. The actual shape, it is some sort like this. And you might be thinking, why is it that? The thing is, when the pH is at the like mid part, or when the amount of volume is less than 17.9, I'm writing in a rounded figure, one to like nearest to one decimal place. So at that point, the pH, the material gets neutralized, isn't it? At that point, the acid base, it behaves in such a way that the change is drastic. Have you seen the like the state change curve of let's say solid to liquid? What happens as the like let's say, how do I say? So as the like temperature increases, the temperature of like let's say certain state increases. And suddenly the state changes like drastically. It changes to let's say liquids, so it's like solid to liquid, like and like there are like sudden transitions, isn't it? So this transition is also some sort like that, that the pH is like takes a rapid turn, like the change like this. That's why like we saw in this diagram that one droplet can change the whole color of the solution. That's what it means. Like at value of 17.9, it is already reached like neutralization, like it reaches neutralization point. But as soon as a slight drop adds, like a single very negligible drop can make a like steep difference, sudden difference. So that's how it works. Its characteristic is like this, so nothing to do with that. So that's actually what like how it looks. So if that's the case, that's 0.3. Now we need to find, or we need to know this portion, like what is this range, like the range for this like sudden rise. That's this is actually like 14. This is 0.3 we got to know, and somewhere in middle that's 17. Now there is one thing I need to also clarify, that this sudden increase, it's this sudden, like how can we define, or like what is the procedure to like actually like draw it? So at this 17.9 we need to draw a straight line, a very steep straight line. I'm sorry, like my drawing is not that great here, but let me try to explain it. The curve should actually sort of coincide in a slanted way to the straight curve. This 17.9 should be a very vertical straight line. Let's say this is 90 degree. Okay. So this is a straight line which cuts the x-axis at a perpendicular line. But this curve, this graph, it should be a bit slanted. Like at the mid level, there should be that cut. Okay. So the graph itself is not also like very straight. It's slanted. Like it's slightly bent. This rising part, this sudden steep part, this it's like slightly bent. So that's how it needs to be drawn. And we also need to give the straight line at the position where the required volume is used. So this is the required volume being used. At that point, we need to draw the straight line. So this is how we draw the curve. Here it is sodium hydroxide. Remember, over here on the horizontal axis, there should be the uh, the element or the compound which is being added. So the element, the compound which is in the burette, that should be in the horizontal axis, not the one which is in conical flux. Why? Because HCl is in conical flux and HCl is already 25, and the 25 amount, it doesn't change, isn't it? That HCl, it remains a, like the what I mean is 0.12, 0.125, that amount of mole of HCl that stays there, isn't it? That is already in the conical flux. But little by little we are adding sodium hydroxide. That means sodium hydroxide is being changed, or the amount of sodium hydroxide present in the conical flux, that is being changed. That is actually increasing. So that's what it represents. When in the conical flux the amount is zero, then the pH is low. As the pH, like the droplets added, so the volume of NaOH increases, the pH increases. So that's what, like, the graph represents. So if the opposite was there, let's say HCl was uh, in the burette, and the in the conical flux sodium hydroxide was there, the same thing would happen. Rather in horizontal line, HCl would be there, but initial pH should be high and the final pH should be low. So the graph would be like the reverse way. Okay, so it should be in the other way around. Now this is the pH, final pH value, the the neutralization point. This is the lower pH value. Now what should be this difference? This difference should be from 3.5 to 10.5. So the lowest, like the starting point of the bend is 3.5, and the ending point of the bend is what? 10.5. Now you might be asking, how do I know? Okay, so okay, wait a minute. The endpoint was actually 13, not 14, and we stayed. So yeah, endpoint was 13. Now you might be asking, okay, how do I know if, like, this range of the steep part is 3.5 to 10.5? Now there is a chart we need to remember, that, like, has to be remembered, because that's actually the information which will be helping us in order to find the values, like the, sorry, in order to draw the graph. So let's say writing the column heading. So the reagents in conical flask, then there is the reagent in burette, then there is the element, like the initial pH, then there is this vertical range, which we just which I just like said, and you are thinking I just said maybe randomly, but no, that's the actually part that we need to remember, and the final pH. Now, oftentimes you won't be given the initial and final pH. Okay, so at that moment we need to calculate the way we did just. Okay, in this way we need to calculate the pH values. Okay, so sorry, yeah, in this way we need to find the pH values. Let me do step 5 right as black so that you can yeah. So this is step 5 from here to here. Okay, so what I was saying is, if the pH values in the question are not mentioned, the initial, the final, in that moment you have to find the pH value of your own using the information being provided. But if they have provided you, then use the information which is there. But if no information has been provided to you, okay, no information is given there, let's say this concentration, these volumes, like nothing is given there, but they are say asking you to simply like draw the curve, then use this chart's value. So this chart is the last, like, place to go. But this vertical range should be used always. This is mandatory. This vertical range is mandatory. Now over here, this is strong acid. On the burette you have strong base. Strong, that's represent B for base. We have strong B is the other way around, and strong acid for A. So we have now burette in the, like, acid in the burette and base in the conical flux. Then we can have, let's say, strong, write it in the short form, is a strong acid, and we have here WB, which is weak base, and then we have, let's say, weak base the other way around, and strong acid. And the fifth one is, let's say, weak acid, strong base, and we have strong base and weak acid. So this is like, these are the type of, like, in this manner they can be arranged. So the initial value of pH is always for the conical flask. Okay, so this is for conical flask. This is always in the conical flask. This is also for the conical flask. Like the pH, we can only calculate for the conical flask. We cannot calculate the pH for the burette. So these are actually the values for conical flask. Conical flask. Conical flask. Okay. Now, initial value when in the conical flask there is acid, the pH is the lowest value is 1. The range is from 3.5 to 10.5, which you need to remember. And the final pH, which we found 13, isn't it? But it should be just 0.2 less, which is 12.8. This is always the case. Now, even if we found it using the calculation, okay, you should give it a bit less, slightly less, 0.2 less. This is always the case. Like the portion, which is the final pH, that should be always either 2 less or 2 more. So 2 less, 0.2 less in place of it is sodium, like it is alkali being added, like the alkali is being added to the conical flask, or for the base, like point 2 should be deduced when the final pH is like basic, or when the final pH is very high, and it should be increased by point 0.2 when final pH is in the acidic part. Okay, here the pH is the final pH is in the basic side, isn't it? For the base part, like it is towards the base. That means like it shows that the solution has become alkaline solution. Now, if the reverse happen, the starting is going to be 13, as I mentioned. Third, like initial value always remains solid, like integer value, but the final value is going to have a change slightly. The range is 10.5 to 3.5. Now, what should be the final value? Because the final should be like the pH value decreased. So if the final pH is 1, it should be increased to 1.2. That's how it works. Now, when strong acid in the conical flask, the pH is 1 again. It starts from 3.5, but since the higher end is for weak base, it should be up to 7.5. Like I have nothing to do with these values. These are the values which have been provided. So we need to remember these values. And the final point is 12 actually, but since it is the like towards the higher end, sorry, the final value is actually 11, since but it is towards the like pH of alkali, that means it should be 0.2 less reduced, so 11.8. And if the other way around, the initial, sorry, this is 10.8, the final value is 11, then it's 10.8, and here the starting point is from 11, yeah, from 11, and here it should be 7.5 to 3.5, and up until, since the ending point is at 1, so it should be 1.2. Now down for weak acid. Weak acid starts at 3, and the range is from 7.5 to 11. So starting range is at 7.5. The stiffness starts at 7.5 and it ends at 11. And the end point should be somewhere around 13, but 0.2 less. So 30, instead of 13, it should be 12.8. And the final one is starting at 13, the other way around, which is 11 to 7.5 up until 3, but it should be 3.2. That's the part. Now, what sort of like diagram do we get to draw? In place of, let's say, we have strong, we already saw the diagram for strong acid, strong base, isn't it? Strong acid, strong base, where strong acid is in the conical flask. Now in the second portion, we will see, or the second graph, we will see strong base versus strong acid. That means base is in the conical class. So the graph should be something like this. For like very rough drawing, let's say this is the vertical point, like the volume, and this is the starting increases. Yeah, it goes like this, and yeah, so this is how it works. Starts at 13, ends at 1.2. This range is from 10.5 to 3.5. This point is 7. Yeah, that's how it goes. Now let's come. Okay, so here I forgot to mention this is volume of strong acid. Initially it was like previously it was strong base, now it's strong acid. Now for the third type of graph where it was like strong acid versus weak base. Now over here this portion or like this graph, there's certain things we need to like remember. The starting thing, the starting progress is the similar as before. This was the straight line. Now after this steep rise, up until this part, like after the steep rise, offer, one thing we need to consider or keep in mind is from here this should be slight bend. This should be slight bend in this way. Now, why is it so? Because there is the presence of weak base. Now, weak base, remember the term buffer solution. So here, after the excess amount of weak base is added, like alkaline buffer solution tends to like play its role. So that's why a certain like it will try to keep its pH lower. It will try to like keep the pH value like towards the like it will try to regain its pH, but for up to a certain extent. But after that, the pH will like it will change. Now the final pH we know is 10.8 since like the maximum was 11, so zero point 0.2 less. The range is from 10.5. No, it's from size. It's from 3.5 to 7.5. Yeah, 3.5 to 7.5. So this is 7.5. This starts at 3.5, and that's our 1. P starts at 1. So yeah, now this is volume for weak base. Now if we draw the other way, which is for weak base versus strong acid, this should work fine. Like there shouldn't be any like, curvature. This should work like normally. Here is our, let's say, the straight line, and the initial rise is very sudden, very steep because with weak base, strong acid is being added. Or we can like just draw this the carbo and this happens. Now I can't even draw. So yeah, this is the maximum point 11. The starting at 7.5, ending at 3.5, and the final point is zero point 0.2 more, which is 1.2. And here we have volume for strong acid. Now, if we draw the fifth one, where I'm actually marking this the number with respect to this category, like over here, like the values which have been set over here in this way. So I'm marking in that way that this is number 4, this is number 5, so that like it becomes easy for you to like recognize how it like, for which part, what type of diagram we need to draw. So that the referencing is there. So it's nothing to be very concerned of. So the left with we are left with more with two more. So the fifth one is weak acid with strong base, which should be now we studied for the buffer solution of weak acid, isn't it? Now here will be that twist, or which will be more dominating, and this will actually like make sense. The initial starting won't be like this. Initial starting will be like this. At the very beginning, there should be a very slight bend because of the buffer solution effect. Then after that, there is no more like nothing. The rest of the part remains same. There's nothing like changed anymore. So the final one is strong base. So it's up until goes 13 point, so 12.8. So 12.8. The range is from 11 until 7.5 to 11, and the starting point is at 3. So this portion is actually like the buffering part, which you like. Let me help you mark. So buffering. So that's where actually this car was there. And final, oh, okay, there was the axis mark, which is volume for strong base. And the final one is strong, six number is strong base versus weak acid. So weak acid, yeah. The starting is a very, we can say a very slight bend. Why? The because of the weak acid, which as soon as slight drop is added, it tends to show its pH. But see that the pH is not actually in like changing drastically, since there is like we are actually adding weak acid. So weak acid has very weak effect. So pH is changing very slightly after the neutralization happen. The pH changes this way. With a straight line, neutralization line. So this is the neutralization line, and it starts at pH value of 13. Final pH is 3.2. So the range is from 11 till 7.5, and this is volume for weak acid, isn't it? Yeah, weak acid. Now we can like you can say the first one you didn't draw. First one we draw like we just drew it on the term of the like values we found. But yeah, for simplicity, I can like help to draw. Help you to draw. Let's say the first one could be like this. If we use the chart value, so it will be like very simple. Let's say this is the straight line, and these are the normal like curves. So that's basically it. This is the starting point, which is 1. The final point is going to be 12.8, and the difference or the distance would be range should be 10.5 from 3.5. This is our volume of strong acid. Sorry, strong base. I'm really sorry. This value for strong base which is being added. So that's the part. Now the next part is the half neutralization point. Now this is the point where the straight line so far I have been drawing. This is actually the portion where the neutralization happens. This is actually the portion where the neutralization happens. Before that, there is the term which is actually the half neutralization point. Like after explaining, you will get the gist. Let me at first explain this term. So half neutralization point. So what is half neutralization point? This is when pH equals to pK in that equation plus the log base 10 of salt over acid. From here, when the concentration of salt and acid, salt concentration equals acids, that's when our half neutralization point is reached. That means the pK value is equals to pH. Why? Because if these concentrations are equal, they get cancelled out and we are left with 1. And we know log of 1 is equals to 0. So that's actually what it is. So pH equals to pKa plus log base 10. Let's say these are actually x, since they are equal. So x by x equals to, this is actually pKa plus log base 10 of 1. So we are left with pKa. Therefore, pH equals to pKa. So this is actually the part. Now, using the equation, let's say Ka. Now, this is an example. So Ka is equals to, let's say, use a example of CH3, like ethanoic acid. So CH3COO minus divided by CH3COOH. Now, if this, if the concentration of CH3COO minus equivalent to or equals to CH3COOH, then what will happen? Then over here, this two will get cancelled out, isn't it? That means Ka is going to be what? H plus, isn't it? So if Ka is equal to H plus, we can write negative log or both the sides. So if we take log for one side, it's mandatory to take the same log for the other side. So negative log Ka. So if even if like I don't give 10, any in question nothing is given, consider it as 10. Oftentimes you will see they write it just simply by Lg. Also consider at that time that is equivalent to Log base 10. That's the same thing. Like so, even if they don't write the base, consider it as 10 because in chemistry the base is only 10. Now, sorry, this is actually H plus. This is concentration for H plus. And if that's the case, then we can say this is actually equals to what? pKa equals to pH. Because negative log function is what? pKa, like the p terms, isn't it? So that's it. Now, if we use this, like, well, if we try to like find the neutralization point, finding neutralization point. Now, how do we find it? Let's take an example of a conical flask where from burette with drop by drop we are adding, let's say, we're adding drop by drop of sodium hydroxide. Let's say in conical flask we have this weak acid CH3COOH, and over here we have potassium hydroxide. Let's say the concentration is 0.68 mole per dm cube, and the concentration for our ethanoic acid is, let's say, 0.5 mole per dm cube, and the volume is, let's say, 25 cm. Okay, they have given us the value for Ka equals to 1.7 into 10 to the power negative 5. Now, remember, do keep in mind that this Ka is actually value of what? Our acid, isn't it? It's the value for the organic part or the weak acids part. So don't forget this Ka is not actually the value. Like the Ka cannot be actually any value for the weak bases, or it cannot be values for other things. So it is going to be the value for weak acid dissociation constant. So if we try to find the initial part, like initially what do we know? Initially the Ka is equals to what? CH3COO minus and H plus divided by CH3COOH. Now, how do we know that? Because obviously the dissociation equation, we know already that the reversible reaction CH3COO minus plus H plus, isn't it? Both of them are like aqueous. All of them are aqueous solution. Now we do assume what the concentration for CH3COO minus and H plus is what equal. So using that method, like using that term, so if CH3 COO minus is equivalent to H plus, then we can simply write Ka as what? H plus square divided by CH3 COOH, isn't it? So this is for the initial part. Now if we simply try to find the concentration for H plus, then make subject H plus and doing square, like taking everything on the other side and doing like square root gives us this. Now we do know the constant, like initial concentration for what? The CH3COH, which is this one, and the Ka value is given. So if we plot, or if we find the value over here, try to find the value over here, we'll get root over of 1.7 into 10 to the power minus 5 times 0.5. This should give us a value of 2.915 into 10 to the power minus 3. This is the concentration for H plus. Now, trying to find the pH value, which is negative log base 10 of 2.915 into 10 to the power minus 3. This should be equivalent to 2.54. This is what our initial pH. Now, as this CH3COOH reacts with KOH, what do we get? CH3COOH, sorry, COOKA, potassium. So K, only K, sorry, no K, so only K plus H2O. Now after this reaction, we no more can like use this term, isn't it? Like use this assumption and this part, isn't it? Remember, we did it like before like the last lecture. So before last lecture or before like this, like 2 lectures ago. So in that way, in that case, what do we need to use? We need to use this formula of pH equals to pKa plus log base 10 of salt by acid, because now we have a salt here, salt by acid. So we need to use that like that over here. Now from here we can try to find the CH3, like the mole of CH3COOH. CH3COOH, the what is the mole for CH3COOH? We can use this information and try to find the mole for CH3COOH, which is actually 25 into 0.5 divided by 1000, which gives us 0.0125. Now using this value, we can simply do the molar ratio with KOH. So CH3COOH is to KOH is equals to 1. That means KOH is also equals to what? 0.0125. Now, in the previous information, they have given us the concentration for potassium hydroxide. So using that to find the volume for KOH, we would get 0.0125, this is the mole, divided by our concentration, so 0.68 into 1000. This should give us a value of 18.4 cm cube. That means this is the value for our neutralization point. So far, like up until now, we couldn't write this neutralization point values, isn't it? Now, this is the method. By using this method, which we just used, in this method, we can find this neutralization point, and we can simply place the value over here. And that will be the end of our like the diagram, like the final part of our diagram. So in that way, let's say if the like what were we using? We are using weak acid with strong base. Weak acid was in the conical flask, and the strong base was in the butyrate. So over here, strong base. So yeah, volume of strong base. The strong base required was what? 18.4 we just found. So this was our neutralization point value. And we can like if we like we know the initial pH was what? Initial pH we found it was 2.54 over here. This was 2.54. So the initial pH was here 2.54. And since it's a weak acid, so weak acid we know from our graph back here. So weak acid versus strong base, there will be a certain bend, giving this, the slight bend, and it goes, and it have this steep part, then it increases. Now the final point is going to be, since we have no information like regarding the what is the final like what is the total amount of sodium hydroxide being used, sorry, potassium hydroxide being used. We just have the concentration, so we can use the value for the chart from the chart, which is what the final value should be 13, but zero point 0.2 less since it is being poured from the burette. So 12.8 is going to be the final value, and this range is going to be what, uh, from 7.5 to 11, isn't it? Yeah. So that's our like the values. Now you can say like why 2.54 is being used. As I've mentioned, for the portion where information is given, use that like use the information provided in the question. If no information is provided at that moment, use the values from the uh, chart. Now, since our the final values and these ranges were not given from the like in the question, so we'll be using that from the chart. But remember, these chart values won't be given to you. You have to keep in mind your like the chart. So this is a like very short topic, like the transit, like the titration part of A levels is very short, but like you have to remember it. So, but once you remember it, the marks are very easy to beat. Now, the last part of this titration is equivalent point. Equivalent point. Now, equivalent point is which one? It is like when acid reacts completely with the base, that's known as the equivalent point. Now, which one actually am I talking about? This is the point of the like this is the equivalent point. This is the equivalent volume we found, but at which point this occurs, that's known as the equivalent point. So this is the equivalent point, which is actually acid plus base reacts completely. Now, for strong acid and strong base, the equivalent point is, let me write it as short, which is E dot P. Equivalent point is going to be, the pH value is going to be 7. So this is the pH value actually. And for strong acid and weak base, the equivalent point is going to be 5. It doesn't matter where like where are the elements are they adding being added from the burette or the like chronicle flask. Like simply just what matters is what are the elements. So if the combination is as a solid like strong acid and weak base, then the equivalent point should be at 5. So when the pH is 5, let's say for here strong acid and strong base. So strong acid and strong base over here, this one. Yeah. So over here, this one, strong acid and strong base, this equivalent point is going to be at exactly 7. But if it was a strong acid and, oh, let's say strong acid and weak base, strong acid and weak base is over here, strong acid and weak base, then the pH should be at 5. 5. How do I know that? We just found I just gave the information from here. So you also need to remember this part. So strong base with weak acid, that equivalent point is going to be 9. So these are like the values which you need to remember. And previously I was like talking about the indicators. So I'll give some information right now about indicators. So indicators, usually we use 3 types of indicators. One is pH. Uh, one is methyl orange, then another is phenolphthalein, and another is methyl red. So indicators are better known as universal indicators. They are weak acids which get partially ionized. So this is the general equation where HIN is the acid, and when it partially ionizes, it forms H plus I minus. It ionizes. So it partially ionizes and forming the partial H plus ions. Now there are 3 types of like indicators. One is methyl orange, phenolphthalein, and methyl red. Now when they are in their actual state, they have certain color, and when they're ionized, they have certain other color. Now this color is based on actually like the anion. So this anion, when they are ionized in their ionic state, like when they're dissolved, at that moment they actually show this color. Now at a lower pH value, so at the low pH value, the methyl orange has a color of red color, and at high pH it shows a yellow color. Then phenolphthalein at the lower pH it has a colorless, like it doesn't show any color, so it has a like watery color. And at the higher pH it shows like pink color. And methyl red, it also shows a red color in lower pH, and higher pH it also shows yellow color solution. Now, in lower pH means in the acid, like when we place it in the acid, it shows red color. Like in the methyl orange, it shows red color in acid. Phenolphthalein, it shows color, like it shows no color. And methyl red, it shows red color. But in alkaline solution, the pH is yellow for methyl orange, pink for phenolphthalein, and also yellow for methyl red. Now the pH range, like for the pH range from where to where it works, it is from 3.2 to 4.4. Like from like in that range, it is better for like using this sort of like if the let's say the neutralization of the product, let's say sorry, if the neutralization of the acid base is in between this range, that means if we can use these values which are the like the equivalent point. So if it is within this range, then that means we can use methyl orange. But if the neutralization point is between this point like 8.2 to 10, then it is better to use phenolphthalein. And if the neutralization point is between this 4.2 to 6.3, then it is better to use methyl red. Now the end point, which means this is the point where methyl orange like transfers its like color, it changes its color completely, and there's no more like it won't change in its color anymore. That's the point like where it will change its color. So that means 3.7 like it is the best point to like for methyl orange to like get the color. So that means methyl orange work at very lower pH values. Then phenolphthalein, it works at very higher pH values. That means those which have like higher pH values, for example the solutions, if they have strong base and weak acid, in that sort of solution phenolphthalein works better. Then methyl red, it works in the range of 4.2 to 6.3, which means in the range of like strong acid and weak base, it works better. And there is another left behind, which we think any one will work better, which like you, phenolphthalein and methyl red, any one would work better for pH, like the solid base and solid acid. So strong base and strong acid. So any one like would work the like better in that way in strong acid and strong base. Now what we are left with is the portion of any like the portion where we can try to see what actually happens in weak base and weak solid acid, that sort of thing. Let's say ammonia. Now ammonia itself is a weak base. Now how this happens? When ammonia ionizes, it forms what? NH4 plus. Now NH4 plus is a strong conjugate acid. Now remember one thing, the thing like the like the part or the component which forms like which works as a base, when it like reacts for and form the product, liquid product. Let's say it's broken down into water forming NH4 plus plus OH minus. If this is a weak base, the opposite to it is what? It formed NH4 plus. So that works as a conjugate, like its conjugate. That's what it is known as. So it's conjugate. And if it is a base, the conjugate is going to act as a acid. So if it is a weak conjugate, like weak acid, sorry, if it is a weak base, the conjugate is going to be a strong conjugate acid. Now, water in this case is acting as what? A base. That means water on the other side forms a what? Strong conjugate acid. Because why? This OH minus is willing to gain like H plus. Now you might say OH minus, isn't it a base? Yes, but in this equation, the way like the character is like this. Like try to think if NH3 is a what? It is a proton gainer. It gains a proton. Proton is what? H plus. So it is gaining a hydrogen ion. So if it gains a hydrogen ion, I mean this NH3, if it gains a hydrogen ion, that means what? It's a proton gainer. So the proton donator is what? This H2O. Now on the other side, if we go on the right hand side, now if we like take this into consideration, what do we see? This NH4 plus have a excess of H plus. Now there H4 like H plus is going to like this NH4 plus is willing to donate a proton. Now the tendency for NH4 plus to donate a proton is very high, that it acts as an acid. On the other hand, this OH minus, the tendency to gain a proton is like so much that it acts as a conjugate, like strong conjugate base. Sorry, strong conjugate acid. And yeah, sorry, this is a strong conjugate base. I'm really sorry, I'm messing it up. This is actually a base. This will remain a base, but this water, this will remain a acid. Sorry. Yeah, actually, this was correct. So this is a base. This is a acid. Over here, this is a acid, but this is a base. So I did a like something, I messed it up. So basically NH3, this is a weak base, this is a weak acid, but on the other hand side, the one which was formed from weak base is now a strong acid. The one which was formed from a weak acid now is a strong base. So the pH will be lower. Why? Because this is a weak base. Now after this reverse reaction happened, NH4 plus is formed. NH4 plus is strong conjugate acid. This will willingly donate proton, isn't it? If this willingly like donate proton, that means more H plus will be there, because this is an acid, strong acid. So this strong acid will have the impression of like providing more H plus to the solution. That means the pH will remain lower. Why? Because more H plus means more concentration of H plus. That means lower the pH value. If same we think for, let's say, CH3COOH, this is a weak acid, isn't it? This is a weak acid. Now when it dissociates in ion, like in sorry in solution CH3COOH, that time it forms CH3COO minus plus H plus. In the previous part, try to know, like try to make the same thing as NH3, like breaking it down in this way. Let's say over here we have one H plus, then we just have NH4 plus. Now try to think it in this way, like rather than having a OH minus here, try to think it in this way. This will like, then you will like make sense, like you'll think it, yeah, it is actually making sense. Now over here, seeing when CH3COOH is broken down, it forms CH3COO minus and H plus. Now this is a weak acid, isn't it? Now this is going to form a what? A like strong conjugate base. So now this is a strong conjugate base, strong CSGB, strong conjugate base. Now this reacts with this extra H plus in the like solution. If there is like if extra H plus is added, when extra H plus is added, as we have mentioned, like how does the buffer solution work? So when extra H plus is added, this conjugate base now reacts with this, like this H plus reacts with this conjugate base, strong conjugate base. When they react, what happens? The equilibrium, like the acid and alkalinity, like they cancel out, and what happens, the pH would be higher. Why? Because we have now greater amount of like strong base, conjugate base, so H plus value will be decreased. Extra H plus which has been added, now that is going to get reacted up, isn't it? So pH will remain high. And over here, what was happening, if let's say NH3 plus OH plus was like, if H plus was added with it, like if it is a base, weak base, it reacted with H plus to form NH4 plus. Now this is a strong acid, it is a strong conjugate acid. This strong conjugate acid is going to react with extra OH minus which has been provided, isn't it? Extra base or extra OH minus. Now OH in giving more hydroxide means what? pH is going to increase. But since OH minus is added extra and we have this strong acid, they are going to react. Thus, OH minus is like the influence of OH minus, it is going to be like diminished. Hence, keeping the pH value lower rather than like increasing with like the addition of OH minus. Since OH minus is used up, the pH will remain lower. Now, in the half of the like solution, when half of the solution reacted, so that means CH3COO minus and CH3COOH, the concentration of them are like equal. At that point, what happens? We have already seen H plus, the concentration of H plus, and this is CH3, let's say CH3COO minus and CH3COOH. That means what? That means we can write instead of this as H plus, and there's X divided by X, so X cancels out, and we have H plus. That means K is equals to H plus. So negative log base Ka equals to negative log of H plus concentration. Therefore, Ka equals to pH, or the other way around. So that's basically it. And we can like for the buffer solution, I can give a like short equation to remember, like to make you remember. Let's say we have this salt CH3COONA. This what dissociates CH3COO minus plus Na plus. We have already studied this, but for the simplicity, so CH3COOH, and this forms this dissociation of CH3COO minus plus H plus. And now what happens is, for the buffer solution part, we have which components in the like equilibrium or in the solution. This like this part, this is CH3COO minus, and we have CH3COOH. Also we have, let's say, H plus, but let's consider these two parts first. Now in buffer solution, let's say if extra H plus is added, what is going to react with it? CH3COO minus, it is going to react with it, producing CH3COOH. That means this H plus, increasing of H plus, like that power is like diminished. Why? Because CH3COO minus actually reacted with it, so pH didn't change. Now let's say instead of that I added OH minus. Now this OH minus is going to either like react with H plus, but for the simplicity, let's say it reacted with CH3COOH, the acid. Then what is going to happen? Simply CH3COO minus going to form plus H2O. That means it reacted with that extra OH minus. So pH, like it didn't let the pH to increase. That means the pH remained what it was. Or the other reaction was what? OH minus plus H plus. If we write in this way, if we make this H plus react with this OH minus, then H2 will be formed. The change in pH will be reduced. Thus, the pH remains what it was, and the buffer solution works in that way. So that was for today. Inshallah, we will start with the organic chemistry in our next class. Take care.